So what are the basic gates? And, or, NAND, not. Okay, those are the basic gates.
What about the gated tag of the other test?
Not on this test. What we're trying to do now is we're working on the positive logic, and then we're going to move into the negative logic. Yeah. So what you need to do, like I said, is the left side there, which is the positive logic symbols. Those are the ones y'all need to really be looking at. The thing that I gave y'all in class. Now you have to understand there's a lot to an AND gate, and there's a lot to a OR gate, or a lot to an inverter. We're dealing with a logic called TTL logic, which stands for transistor logic. And what that means is we're going to input into transistors and we're going to output off transistors. So the way they basically work, and what I'm going to do is draw a standard TTL inverter. And I think this is in your textbook somewhere. And then they put a diode right here to protect the input ever going negative, because that could really cause some problems. So this is a standard TTL inverter. Fortunately, we represent it with this symbol right here. So what we're doing, and this is solid state, we can do this with relays, but relays are electromechanical, right? And they take a lot of current. This is a typical, and the output comes right here, I'm sorry. So there's our output. So what we're saying, if this transistor right here goes bad, we don't troubleshoot it as a transistor, we troubleshoot it as this guy right here. So what we would do is, if it was bad, we got one of two options. So this thing, standard 7404, this is the one we're going to deal with. And it comes in a 14-pin dip. 1, 2, 3, 4, 5, 6, 7. And then they should be parallel with each other. 1, 2, 3, 4, 5, 6, 7. And how are they numbered? We find the notch, or we find the little dot. And this would be pin 1, 2, 3, 4, 5, 6, 7. Then we come over like this, right? And it goes 8, 9, 10, 11, 12, 13, 14. And that's the way they're numbered. Some of your, and I'll try to find the pin out of the, like the i7 processor. There's so many pins on that they assign rows, letters of the alphabet, and then they assign pins numbers. So it'd be like B37. So it'd be row B, row B, pin 37. So some of these microprocessors have hundreds of pins, which is pretty neat. Now what they do is they come in here, and of course the pin out of this is inside your book, right? 7404 should be the front page. I mean, I'm right inside the front cover. And if you hadn't got your book, you can always look them up online, right? And what they do is they come in here. How many would be inside a chip? How many be on? So that little chip is in the center, but we don't ever see that. All we see is the pins. And of course, this is looking at it on the top, right? You understand? And how many of them would there be in here? Huh? Yeah, we have 12 connections, because why? Yeah, we get the input and the output, and the power is shared. So the power is shared inside the circuit. So that would be 6 in here, right? And they're in there like this, if I can draw them. And then this right here, they label ground, but it's actually can be common, yeah. And then over here, they flip around and come around like this. Oops, I skipped over a pin. And then this right here is labeled DCC. Now in digital, in solid state, DCC can be any DC voltage. But in digital electronics, this is going to be 5 volts. Plus or minus 5%. So it means this could legally be anything from a 4.75 volts all the way up to 5.25 volts, and that would be considered okay. Okay. The outputs actually are formed across these guys right here. And we'll go over later on what happens, how these things cascade. But what's going to happen is either this guy right here is going to provide the high, and this guy right here is going to provide the low, and they're never going to be on at the same time. So it's set up so they switch, and they're going to switch at a certain voltage, right? You understand? So they'll never be on at the same time if the thing is working okay. Now what we do for an AND gate, is we would come in and add another emitter. So this would be for a 2-input NAND gate. And each one of them would have its own protection diode. And then of course, so what we do on NAND gates is we just add more emitters. So it's the same basic circuit, it's just that the transistors have multiple emitters on them. But what I want you to know is we input on transistors, we output on transistors. So this is why this is called transistor logic. So DTL, what would that mean? Well, it means we input on diodes and we output on transistors. And that was a phase we went through. RTL was a phase they went through, where they input on resistors and output on transistors. But what we're going to do, this would be represented with this symbol right here. So that whole circuit is represented as a symbol. So what I've got to get to, the circuits themselves are fairly complex. And we do need to understand this so we'll know how to figure out if it's bad or if it's good, right? You understand that. But we're going to troubleshoot it from a level point of view and not from an internal circuit point of view. And we'll look at some of the circuits when we get into the MOS, the metal oxide semiconductor gates, and we'll look at those too. But it's basically the same. An AND gate is an AND gate. A NAND gate is a NAND gate, right? You understand that? And if you see that symbol, it could be ECL, it could be TTL, it could be anything, but it's all going to do the same logic. So this is a symbol for a 2-input AND gate, right? We already looked at this. Everybody okay with this? Just drop back and review a little bit. You know, what do we say about this guy? What's the phrase? No, what's the phrase? Yeah, all highs equals a high on. So if all inputs are high, the output would be high. This is a stripped down version. And then on this one, the equation would be X is equal to what? Yeah. Legally, you're not supposed to say that times, because times is math. This is not math. So this represents a what? Yeah, that represents an AND. So in Boolean algebra, we don't say A times B, we say A and B. It's just that you know what we used in math to represent multiplication, we use that in logic or Boolean algebra to represent AND. Of course, this is 2 inputs. How many inputs could we have? Huh? We could have a lot. Maybe not as many as you want. We do have the ability, by the way, to do something like this. So we can combine these things. So what I'm doing is I'm using 2-input AND gates to get a 3-input AND gate. So I can use an 8-input AND gate and run it into another 8-input AND gate, and that would give me 15. That would be like a 15-input gate. So we're still confined to that right there. And if it's a 14-pin deal, we got 12 pins to work with. So the maximum we could possibly have, would be 11 inputs, right, and 1 output. That would be it. in a 14-pin deal. So you can't say as many as you want, but in an IC, but we can cascade these things and probably get as many as we want, right? And if you got a lot of money and you're going to sell 1 million of these things, you could probably get a company to make you one that's got as many as you want. This is what we call a truth table. And what a truth table does is it shows us what the state of the output with all combinations of inputs. Right? Everybody okay here? So and, or, everybody okay here? I know these figures might be right, I'm not sure. I think the output at X will be high whenever input A or input B is high. Or we use the term any, right? And what do we say? Any high equals a high. Okay, you understand that? And then we use this sign in math that we use, this symbol. Now you understand it's a symbol. Yeah, it's a symbol. And a symbol is used to represent something. So in math, we use that symbol to indicate addition. In logic, we use that symbol to represent a what? An OR. If any input is high, the output will be high. So any high equals a high. So this is the shorthand method, right? This is a symbol for a 2-input OR gate. So we start off with the back. It's got a concave to it, and the other ones are arced. So we have people that get these symbols so they look very similar. One of them's the shape of an uppercase D. And this is not the same, right? You understand that? By the way, legally, these lines are supposed to touch. So this could have, OR gate's got, OR logic, it's got at least 2 inputs, right? Could have a lot, but at least 2. This is the truth table for the OR. Are we okay? Yes or no? We're just going back and reviewing. We already went through this, right? A lot of times, especially in computers, we need to, let's find this in the book. Make sure I'm giving y'all the right. So, timing analysis. We're going to show you all logic analyzer. Let's see if they show you some of those. This is figure, this is on page 71, I believe. They got some good ones on page 70. And believe it or not, we use these even when you take motor control. We use these in motor controls. It always surprises me people have a problem with these timing diagrams. So this is an and what we're doing is, notice what we're doing. So what we're doing is we're taking one input. Let me find my blank sheet. Where's it at? Right here. So later on, we're going to run into some integrated circuits that have enable inputs on them. So if we disable them, they don't work. If we enable them, they're allowed to work, right? You understand? An AND gate is a very popular circuit to use as an enable circuit. So right now, we'll start off with one input. And then what we're going to do with this guy is we're going to hook it up to a switch. Let's do it this way. So normally when we use a switch in digital, we have to supply a true. So if I came over here on TTL and I put that switch right there, if it was open, what would the gate see it as? Huh? Now we'll learn this later on. It's a nothing. It'd be what we refer to as a floating input, which is not good. Okay, y'all understand that? So what we do in digital logic is we make sure that the gate gets a legal high and it gets a legal low. So in digital, you'll see this used a lot if I'm going to put a manual switch on the thing. I'm going to come over here and I'm going to put a pull-up resistor. And we're going to connect that to VCC. And then my switch is going to be over here. And it's going to provide a common. So now if the switch is open, then there's nothing, no current flow to drop any voltage. So I would get a 1 right there. And when I close the switch, I get a 0. So you see, this is a common switch. Because in digital logic, we're not supposed to have any what we call floating inputs. We either got to put voltage on them or we got to put ground. I understand that. So I'm going to come over here, and right now, let's come up here and close the switch. The switch is closed. Okay. Now let's say I have a stream of pulses coming in on this input right here. What would I see on the output? Huh? Shoot, you're right or wrong. Who says I'm going to see a 0? Keith says a 0. Who says I'm going to see a string of pulses? Huh? Huh? String of pulses. Oversay. What do you say, Corinne? A 0 or a string of pulses? 50-50. 50-50. It don't cost anything. On test it would, but this don't cost anything. In class, this don't cost anything, right? You understand? You're either right or wrong. So this guy either is going to give us a 0 out, or it's going to get us a string of pulses. So either I've got the gate open or I've got the gate closed. Huh? Kareem says 0. Who says 0? Raise your hand. Who says a string of pulses? Okay. First of all, we need to look at this. It says it takes all highs to equal a high. By George, I got this guy right here connected to what? A 0. So if that one input is connected to a 0, there is no way, shape, or form I could ever get all highs. So we got the gate closed. The cows can't get out. And this is why they're called gates right here. Okay, you'll understand that. So we got the gate closed. So if you said all 0s, that's great. That's what it is. Because it says it takes all highs to get a high. And there's no way in the world I can get all highs if I got what? If I got one of my inputs connected to 0. But when we come over here and we open this up, now it allows us to get a what right there? A 1. So now every time the input goes high, we have all highs. The output would go high. When the input goes low, we don't have all lows, all highs, and the input would go low, right? I mean, like this. So what it's going to do, it's going to duplicate the input. So using this guy right here, I'm going to call this an enable. So what I can do, I can control the enable input, and I decide when it gets through and when it don't get through. Okay, you understand that? What if I added another input? Well, now if I enable it, it acts like a 2-input AND gate with an enable input. If I disable it, the other 2 inputs are just flat ignored, right? You understand? So with an AND gate, no matter how many pins it does, I can use that enable input to either open the gate or close the gate. So that's why we refer, this is mainly the reason we refer to these things as what? Gates. So as we move through here and we start getting to these more complex chips, you're going to see some of them have enable and disable. One perfect example is in a computer. I can't have everybody on this bus we call the data bus all the time. How many things can be on the data bus on a computer at any one time? Well, how do we keep all those guys off of it? Well, we disable them and do what? Enable. So we have a special circuit called address decoders. It's inside the chipset now that looks for addresses. And when the address for this device comes out, it'll enable one device and everybody else is what? Disabled. Kind of like the mailman or the mail person coming up to your mailbox. So they usually only get into one mailbox at a time, right? You understand that? And that's basically what address decoders work. Okay, so this would be an AND enable. Okay, so let's change this over to an OR gate with two inputs. So I'm going to keep this bottom circuit the same. A 2-input OR gate. So what would the output be? It's not going to be 0, guys. What's it going to be? So is it enabled or disabled? Well, this says any high equals a high. No, it don't say see the pulse. It says any high equals a high. So this output's going to be sitting up here. This is solid as a line. It's not going to be doing anything. Because do I have any high? Okay, I have the switch open. If the switch is open, then this resistor is going to pull this up. That's called a pull-up resistor, by the way. So what we got on this input right here is we've got a solid 1. Is that any high? Is that any high? Okay. Is this any high? Yes or no? Yes. Yes. I know some of y'all answered that, but some people was doing that. Yes, it's any high. If I have any high, the output is what? High. So right now the gate is closed. It's just that an AND gate puts out a 0 when the gate is closed. An OR gate would put out a 1 when the gate is closed. So how do I open the gate? I close the switch. So we close the switch. That puts a 0 down here. Right? You understand? So what's going to happen now? Well, any high equals a high. Is the input high right here? Right here. Yeah. Okay, so what would the output do go? Yeah, it would go high. Is this any high? No, so the output would go low. Is this any high? Yes, the output would go high. Is this any low? So what we do now is we just open the gate and let the cows go out. So an OR gate, we get a high if it's disabled. An AND gate, we get a low. And it all depends on what type of light. It all depends on who's down here. What do they need down, whoever this guy feeds, whatever it needs. If I come up here and add another input, then we can disable it with one input. If I enable it, it acts like a 2-input OR gate. So if I had 4 inputs, I could use one for it to enable, and then when it's enabled, it acts like a 3-input OR gate. But later on, we're going to get into these circuits that we're going to look, and when we look at them, by the way, all combination logic is drawn as rectangles. We're going to come over here and we're going to see something called E or CS or chip select or something like that, and that's all it is just an enabled and disabled circuit. And when we start getting into a lot of combination logic, they're not going to draw the individual circuits like we did for the inverter. Because if we know how it works, we can't fix it anyway, right? If it breaks, what do? We replace it as a chip. If you got one OR gate go out, then you replace all of them. If you got a spare, you may be able to swap over to your spare, but that's real hard to do on a printed circuit board. So what they're showing on this slide right here is that feature right there. So this is an AND. So we got an enable. So right here they're showing when the enable is high, what does the output do? The output follows the input. When the enable goes low, what did the output do? It goes low. Over here on the OR gate, when the enable is high, when the enable is high, the output stays high. Right? You understand? So an OR gate gives me a an OR gate gives me a low active enable. A AND gate gives me a high active enable. Does that make sense? Okay. So here it goes low, so here the output follows the input. Here it goes back to high, and the output goes high. Now, which one you use depends on what that guy right there needs, right? Does that make sense? So on page 70, I wish they would have put that in the PowerPoint. It should be figure 15 and 16. We've got one of these, by the way. I'll have to pull it out. On page 68. Of course, if you don't have your book, I know they had problems getting it. You need to find some place you can look on, right? Figure 310. The problem we have when we try to monitor all these inputs, a logic probe, how many signals can we monitor at any one time using our logic probe? One. So if I've got an 8-input AND gate and it's changing, it would be almost impossible for me to see all highs equal high. Now, an oscilloscope, a standard oscilloscope, we can look at two things, which means I could look at the two inputs on a 2-input AND gate. If I got a 3-input AND gate, then when we moved over, we don't know what's going on with the other one. We have a device called a logic analyzer, which we'll pull out and let y'all see. These guys are very expensive. We got one that's fairly cheap. I'll show you that one. I don't even think it's they make it anymore. But on that one, we can look at this. We have a 32-channel logic analyzer. So what does that mean? We could actually look at 32 signals at the same time, which is pretty neat. I'll show you that. A picture of a typical logic analyzer. Let's show this on figure 3-10. We have a simulation program called Electronic Workbench. And what it does is it's a simulation program. It's really slick. And what a simulation program does, it allows you to simulate a circuit and see how it will react before you buy the parts to build it. So these things are pretty expensive, but if you were in the process of designing digital circuits, then these guys right here will be a really good tool. It's not on my computer. I'm on that computer over there. That's taking too long. So simulation, they're showing you a typical simulator in figure 3-11, where we pull down parts, we wire them up, we wire them with symbols, not with actual chips, and then you can bring in a simulated logic analyzer. Y'all can see how that works. So this is a 7408. Y'all should have the pin out. So the 7408 is a quad 2 input AND gate. And I don't know if that was inside y'all's parts kit or not. Y'all remember on the inventory the 7408? Yeah. So that's an AND gate. And remember, what we start off with is we start off with 74. And then we usually come in here and put designators. And then it could also be like this. So what do these center designators indicate? Anybody remember? Yeah, it indicates to us the power and the speed. And so what I was saying, if all you need is the pin out, you could look up any 7408. So a 7408, which is the standard, would have the same pin out as the 74S08 or the 74LS08 or 74ALS08 or the 74AC08. They would all have the same pin out. Now, if you're trying to figure out what this guy right here can drive, and what's a legal high and what's a legal low, you'll need to look that information up, right? You understand? So this is a 7408, and so it's got how many gates would be in here?
No, it'd be 4.
Yeah, it would be 4, and I'm pretty sure if you got the 7408, they're positioned like this.
So why do you have to do 3?
Wait a minute. It's a quad 3 input. 3. It's a quad 2 input. Did I say 3? Input and gate. So a quad 2 input and gate requires 3 pins, right? And of course the quad means there's how many in there? There's 4. So this is,
I'll count the leads.
well, it's only 3 leads. Yeah, so remember on these gates, we lose 2 pins for power.
Oh no, this is just I had 6 when we first started.
Well, that's a hex inverter, but a hex inverter only needs 2 pins because an inverter is the only gate we got. That's not true. Later on, we'll look at this guy right here. The book don't cover this, but we need to learn that. This is a device we refer to as a buffer. And we'll look at what that's needed for later on. It does no logic, but it's got a use. I mean, we run into these all the time, buffers. But we don't. A lot of books don't cover buffers because it doesn't do any logic. So it's not one of the 5 basic gates, right? You understand? Even though it is. So this right here would only require 2 pins. So a buffer and an inverter are the only 2 gates that only requires 2 pins because all they do is invert, right? All your other logic, your ands, your ors, your nands, your nors, those all require at least 2 pins. 2 pins for inputs. And we got to have what? Got to have 1 pin for an output. So when they identify the circuit, they identify the number of inputs because they take for granted, you got to have a what? Output. I mean, it wouldn't be any good not to have an output. That would be like having a calculator without a display on it. What good would the calculator be? Wouldn't be too good. These days, it's like having a cell phone with the display don't work anymore. I think Maurice broke his display the other night. Yours still works okay, though.
Yeah.
He's just got a little crack in it. So this is how this was how it would be wired up, but what you got to understand, this is kind of misleading, and somebody in this class usually does it, is they'll need 4 inverters, and they'll say, Rich, I've only got 2 inverters in my kit. But what they're doing is they're looking at it as a chip and not as 6 inverters are inside one package. So we have a lot of people that needed to wire this, and then somewhere else they needed this right here, and they say, well, I've only got 1 of these chips, but they forget there's what? There's 4 of them in there. And what the only thing they have in common is they share the same package and they share the same power. You don't understand that? It's just like outlets in your house. The outlets are individual. The only thing they have in common is they're in the same house and they share the same power. So just because you use one outlet up don't mean you can't do what? You can't go to another one. So understanding how many you got in there, usually every time in this class we got one circuit where we need like 4 or 5 inverters, and somebody's going to ask, I've only got 2. I think you've got 2 in y'all's parts kit. And then they say, I've only got 2 inverters, but they're not looking at it. That one package has what? 6 of them in there. Let's move on. So everybody okay? Logic probes. We'll look at this later on. We have another probe that we call a pulsar probe. And what is a logic probe going to do for us? Well, it tells us some information, right? It's got a light that comes on when it sees a legal high. It's got a light that comes on when it sees a legal low. Normally it has a pulse light right here. What does the pulse light tell us? So what does the pulse light do? Yeah, the problem we have is, so we got something like this, and it's sitting there for a high, and then here it pulses low, and the pulse is like for 1 millisecond. Would you be able to see the red light come on that pulse on that probe for 1 millisecond? And it comes on. But our eyes see it what? Our eyes don't see it come on. So what happens is the pulse indicator here, it has what we call a one-shot in it. So what happens when it sees a transition, it gives us out a pulse long enough so we can see that light going. So if the guy is sitting at a solid high, when we see the pulse light come on, we knew we had a what? We had a low pulse. If it's sitting at a solid low and we see the pulse light come on, we know we had a high pulse, right? And of course, if we see a clock, if these are lit up all the time, which means you're looking at a clock, then these both will be lit up and all three of these will be lit up, which indicating you're looking at a clock. But the lights are blinking so fast, your eyes blend them together, right? Or just like they do here. So y'all know these lights are turning off every 8.33 milliseconds, right? Completely off. They are turning off. But our eyes see them as what? See them all the time, because 8.33 milliseconds, our eyes can't even pick that up. And thank goodness, because if our eyes was any faster, we wouldn't have TVs, we wouldn't have motion pictures. Now, no movies are nothing but a series of still pictures, and they put them up there in an array that our eyes just do what? Just blends them together, which is pretty neat. Pulsar probe generates a pulse that will normally override a high or a low. So with a pulsar probe, what we can do is we can force ones and zeros into a circuit. And I'll show y'all that later. So let's look at the inverter. So this is new. So the inverter used to complement. So in digital, complement does not mean, hey, you look good today, or your hair looks great. In logic, complement means the opposite of. So anytime we take the complement of something, that's the opposite of. We use this in solid state when we talk about complementary pairs of transistors. So we looked a little bit at transistors, right? We have NPN and PNPs, but we can get two transistors that have the same specifications, and they're called complementary pairs. So, which means they're opposite of each other, but they have the same specs. So use to complement or invert a digital input. This should be figure 3-27 in your book. So what would be the output? This is a timing diagram for a inverter or NOT logic. So here's my output. So this is the actual guy. So they're calling the input A, they're calling the output X. I'm sorry. I don't know what they're calling. We'll call it X. So let's call it Z because it's down here. So let's call it. Okay, so let's draw what we get. What would we get? So here's the input. So what would the output start at? It's an inverter. The input is what? Low. So the output would be what? High. So I'm going to come over here. Then the input goes high. So what would the output do? Go low. And then we'll go over here and do it. So we'll just come over here and just. Yeah, that's what an inverter is. So an inverter means the opposite of. No, a differential amplifier looks at two symbols. So a differential amplifier looks at two signals. One of them is the uninverted, the other one is the inverted. So we could develop a differential amplifier using a circuit called an operational amplifier. But what we would do is we'd run one of the signals through an inverter, right? You understand? And that would generate the inverted. this is what a differential signal would look like, but a differential signal, you got two lines. This is actually coming in on the input, and this is coming in on the output. So on a differential amplifier, one of them we call plus, one of them called the minus. This is the non-inverted, so that would be, and then this right here would be the inverted. So we get problems with people seeing this as a plus and a minus, right? You understand? But it's a symbol. Y'all remember Prince, the guy that, you know, he had problems with his record company, and he didn't want them to use his name anymore. So what did he do? He changed his name, legally changed his name to a symbol.
Why he did that?
Because the problems he was having with his record company, the people who was publishing his record, and using his name. You know. So he changed his name to a symbol. And they used to call him the artist that has no name. And he had his guitar shaped in that symbol. He eventually changed his name back, by the way. Yeah. Artist does strange things. So you're thinking about this being two signals, but this will be what's actually placed on the watt, Morris. This is placed on the input, and this is what we get on the output, right? Okay. So we're going to start getting into this thing I'm going to refer to as a bubble. And we're going to start using the term high active and low active, which I've accidentally slipped and used that a little bit. So if we use the term high active, it means the symbol is true when it's high. If I use the term low active, it indicates the signal is true when it is low. On symbols, what we do is we use a bubble to represent a low active symbol. So on our NOT gate, notice we have a bubble on the output. So that means when the input is true, so the input is true when it's high, the output, which is low, to be true, right? Understand? So the bubble, to us, is going to indicate a low active signal. Now in Boolean, the way we indicate something is low active is we put a bar above it. Now for years, printers did not have the ability to overstrike. They used to not even have the ability to underline. So what we did for years is we followed it with the asterisk sign. So if you ever get into any older logic books, they'll represent it with an asterisk, and that's still true. Are we okay? That makes sense? So that means if I come over here and do the equation for this, and I call this A, and I call this X, then I'd say A is equal to this, and I'm going to put a what above it. I'm going to put a bar. And what we would say would be, we call this not. That makes sense? Yeah. It don't mean it don't exist, it means it's low. Are we okay? So in our Boolean equations, we'll use a bar to represent that. Or you might see a what? An asterisk. Everybody okay? Yes or no? So a NAND gate. So what we do on a NAND gate, so here, and this is where people runs into problems because the inputs are on the left and the outputs on the right. So somebody in this class is going to put A, B equals X. Somebody's going to do that because that's the way it looks like it flows. But mathematically, that's incorrect because what you're solving for in a math equation is always on the left, right? You understand? So we come over here, so we put the output over here, and then we put A, B. And the way we represent a low active output is we put a bar above both of them. So a bar above both of them means that the output is low active. So if I drew this symbol right here, so if I come over and drew this symbol right here, just for the heck of it, and we call this A, we call this B, and we call this C, then what we would do here is we'd put, we call this X. We'd say X is equal to A and B. So if we put it above the individual characters, we're talking about the input. If we put it across the whole thing, we're talking about the output. So what would this one be? X would equal to A, not A, and not B, not. Now this is not a double negative, because to be a double negative, they would have to be on top of each other, right? So if I put a bar across the whole expression, we're talking about the active state of the output. If I put a bar above each individual term, we're talking about the active state of the input. So right now, if this is a NAND gate, I'd say X is equal to A and B. I don't put any bars above them because they're what? They're high active, right? You understand? But we got a low active output, so I put a bar across those. Are we okay? Everybody okay? Okay, so I look at my inputs. There's no bubbles on the input. So this means the inputs are high, what we say high active. I look on the output and we got a bubble, so we'd say the output is low active. But we got to have the ability to represent this in a math equation. So in our Boolean algebra for these equations, we start off with the input on the left. The output on the left, right? You understand? And then we put an equal. And then we start dealing with the inputs. Well, we got A and B, right? And then how do we indicate a low active output? We put a bar above all the terms, all the input terms. If I've got a low active input, I put an individual bar above that. So if I'm doing math and I come up with this, and I have two bars for some reason, then these two guys right here will cancel each other out, because that would be truly what we call a double negative, right? Does that make sense? Or if I came over here and I start develop an equation, and I came over here and got something like this, then we would say, okay, this would be equal to A and not B, because anytime we got two bars that are exactly the same length, then that's going to be two negatives, and two negatives make a what? Positive. So those rules of math work. But notice I don't have two bars above the B. So the B is going to stay what? Going to stay low active. Are we okay? So this is a NAND gate, and what does a NAND gate tell us? All highs equal to go. Good. So a NAND gate says all highs on the inputs equals a low output. So what would the truth table be? A, B, they're calling the output X. How many inputs can we put on this thing? 4. How do you know that? You say, no, we got two inputs. We can only put two combinations. 2 would be equal 4. So on digital, you can count, you can fit, because all you can put is two combinations. You can either put a low or high on there, right? You understand? So if we got two inputs, we can put two combinations on each one of them. So all you have to do on digital to calculate the number of input combinations is 2 raised to the number of inputs. So if I add one more, how many could we have now? Well, that's 2 to the third. So now we could have 8 inputs. Then what we do is we come over here and just start counting in binary. I'd say 0, 0, 0, 1, 1, 0, 1, 1. Oops, got that. Nobody called me on that. Y'all see what I did? Yeah, I put them on the same side. 0, 0, 0, 1, 1, 0, 1, 1. So what would I have right here, guys? Is this all highs? Okay. It takes all highs to get a 0. So if it takes all highs to get a 0, then what would this be? Is this all highs? Okay. Is this all highs? Is this all highs? Is this all highs? And that would be the function table. So y'all got to look at that. Y'all just can't look at this and see that and want to say low. You got to understand this right here. But what you got to understand, if I made this an 8-input AND gate. By the way, so we have a symbol, and then if we don't have enough room, they just extend this. Now, how many input combinations would this sucker have in a truth table? It'd be 2 to the 8, which is 256. So you think I'm going to do a truth table for that thing? No. But what does it say? It says all highs to get low. So if I came over here like this and come over here and put that right there, the output would be low. Because I don't have what? I don't have all highs. So if any input is low, the output would be. Y'all understand that? Ooh, I just said something that's interesting. I used the term any. So it takes all highs to get a what? To get a low. So if any input is low, the output will be high. I use the term any. What do we use any for? Or? Very interesting. So let's draw that. If any input is low, by the way, on an OR gate, what we do, so this would be, if any input is low, 1, 2, 3, 4, 5, 6, 7, 8. If any input is low, the output will be high. Interesting. But that's what it says, right? If it takes all highs to get a low, no, you can't do it twice. You got to change everything around. So if you say all once, you got to say any the next time, right? You understand? You can't say it again. So if it takes all highs to get a low, then any low will give me a high. And this is where people get confused. They want to see this. They want to see this as an all. But what we're looking for is your all is your unique output. Is this a unique output? No, there's 3 combinations that can give me that. There's 3 combinations that can give me that. So that's not unique. This is your all right here. But for some reason, people want to say that, and they want to say that, they want to say all lows. But that's not all lows. Right? You understand? This is all highs, but that's not all lows. Y'all understand why? Because this right here is the all right here, because this is the unique output. This is not a unique output. So here's a truth table for a 2-input AND gate. This is an OR, guys. Y'all understand that now? Same as an OR gate, except that the output is low active. So here we would say what? So here's an OR gate. So we'd say what? Any high equals a low. And here's an OR gate. Here we'd say what? Same thing. This is an AND gate. What would we say here? I highs equals a high. Good. This is an OR gate. We would say what? Any high equals a high. And ain't that neat? What to me, once you learn those expressions, I think I told you about the guy. He graduated from the University of Alabama. And we were trying to troubleshoot digital logic, and that guy was trying to write truth tables for all the gates, beside the gates. And that's what he learned. He learned truth tables. And I learned what? Any high equals high, any low, and that kind of stuff. It was so much easier because if you learn those, you can develop a truth table from those expressions, but it's hard to express. But if you don't know those expressions, then you have to deal with truth tables. And it gets real hard. So this is the truth table. So here's the Boolean equation. So I start off with the output, then I put the inputs. The plus indicates a what? Or that symbol indicates an or. Yeah, we got it. And then what do we do? To indicate the output is low active, we put a bar across it. And that would be the Boolean equation for an or. So what would be the Boolean equation for a 3-input or? We'll call this A, B, C, and this is a NOR, I'm sorry. And we would call the output Z. So what would it be, guys? Z equals to
A or B or C.
with a bar across over. Okay, all three of them. Yeah, it has to go all across. Don't stop. It's like people stopping short on red lights. I see people stop so far back they don't even get on the sensor. They wonder why the light don't change. There's down at the end of Memorial Drive, you see people will go over the white line and the light, and they're off the sensor and it never changes. And eventually, what they do, they either run the light, or they sit there until another car comes up. When I rode my motorcycle, it didn't have enough metal in it to set off to change the lights on the front gate there. So I'd put my kickstand down and go over and hit the crosswalk button. All right, guys, let's take a 10-minute break. I think that's all the basic gates, right? AND gate. But notice they do the same thing. They just do the whole AND, right? You understand? And then they do what? They put a bar above the whole thing, right? Of course, we wouldn't do a truth table on this, because like I said, that would be 256 combinations in our truth table. So come up and say all highs equal to low, right? Another thing that I need to start looking over these timing diagrams in your book. We're not going to have many on the test, but what these things do and the way they work is that they give us the inputs, and then they have what they call a control or enable input. And then it's up to you to figure out what the output is. If you can understand these, you can understand these gates. If you can understand these timing diagrams. This is on page 83, but they're all through chapter 3. So right before we got to the enable input, so this right here was the timing diagram for a NAND gate, an AND gate, and then they gave the same diagram with the same inputs for a 3-input OR gate. So notice here they label the inputs A, B, C. It's an AND gate, so what are we looking for? We're looking for all highs to get a high. So when I follow this over in this time right here, A is low, so right off the bat that means the output will be low, right? Well, this is not a truth table. This shows you actually what the inputs are. Yeah, so this is A, B, C. This is A, B, C. Yeah, and then this right here would be X. But this wouldn't be a true truth table. Why wouldn't it be a true truth table? Because we don't have 8 input. We don't have 8 different inputs. So a truth table shows you all combinations on the input. So normally on a truth table, what we do is we look at the number of inputs, we raise 2 to that power, and we just start counting from 0 to, so if I've got 8 inputs, 3 inputs, then I would count from 0 to 7, and that would give me all possible combinations. So we've only got 1, 2, 3, 4, 5, 6 here. So that means there's no way in the world this is going to be the true. Understand? We could put the truth table for this signal, but that wouldn't be the truth table for an AND gate. Understand what I'm saying, Joey? But what we're trying to do is this is where the truth table makes sense. So what I could do in a truth table is I could look up this combination right here, and it would tell me the output would be low. But that would be one of 8 combinations, right? You understand? I could look at this combination right here, but if you understand all highs to get a high, then that is not all highs, so it automatically put a what? Put a low. All highs to get a high. Well, A, B, and C are both all highs, so the output would do what? Would go high. All highs. As soon as I see that, the output's going to be low. I don't even have to look any further because it takes all highs. As soon as I find one input of an AND gate low, I don't want to worry about the rest of them. I go ahead and put a low on the output. Does that make sense? I look here. This looks like we're pretty good right there. Oh, but there's a low right there. As soon as I see that low, I'd put a what? I'd put a low. I come up here. I start off with a low. So right off the bat, I'm going to put a what? I'm going to put a low because it takes all inputs to get a high. Here I see this one. There's a high. There's a high. There's a high. So the output would be high. Now here's the same inputs with an OR gate. Now OR gate says what? Any high gives me a high. Is this any high? Well, see, I got to look at all of them now. Okay, low, low. So any input to get a high, so the output would be what? Low. Right here it says any input to get a high. As soon as I see that, I'm not even going to worry. That sucker could have 2,000 inputs, but it says any high to get a what? A high. I'd go down here and I'd put a high. I get right here, I say, well, I'm going to have to go a little further. So that's a low. That's not any high. Right there, I've got any high. So what would I do? I come down here and put a high. I hit this right here. It says any high. As soon as I see that, I would come down here and put the high, right? You understand? Here it says any high. I look at that and I says, well, I go down one more, down more. I don't have any high, so I'd put what? A low. And then, of course, here, as soon as I see that, I would put a high. So this is the timing diagram for a 3-input AND gate. This is the timing for a 3-input OR gate. But it's not a truth table, right? And if you can do this, then you understand that gate. Because this is what we would see on an oscilloscope, right? You know, if this was the pattern on the input, or a logic analyzer would be better. Are we okay? So eventually we're going to have to do timing diagrams on this because that's the name of the game. Taking a truth table or taking an expression and actually determining what the output will be for a real life signal, right? On the this is showing us about logic analyzers. This is showing us what we do need to just touch. We're not going to get into these, and you're not required to know these. I don't even see it in this chapter. But these are the symbols we use here in the United States. Unfortunately, these are not the ISO or the International Standard symbols. The International Standard symbols, this is in the PowerPoint. So let me turn this on. Let me so it says 3-65. It is. No. Okay, it's 3-64. So the table phone, which is on page 95. Can you see? So over here on the international signals, they draw everything in squares. Everything is a square. So notice here, if they put the little triangle output, it means low active. So if they got the triangle on the input, it's going to mean low active. If they got a triangle on the output, it's going to mean low active. Then what they do is they come over here. This has got a 1 in, right? A 1 in would give it a what out? 0 out. Now this is that is the symbol for AND. That's in the English language. That is the symbol for AND. So what would this be? This would be a 2-input AND gate, right? You understand? This says if any input is equal to or greater than 1. So that would be any input. So this is a what? This is an OR. This would be a NAND. And then this would be a NOR. So these are ISO symbols right here. These are international symbols. Now, we're not going to use them in this class, but you need to know they're out there. And there's all type of references for ISO symbols. Now, basically, when you get into combinational logic, the symbols are the same except for what they indicate low active. So in international symbols, a low active is indicated with a triangle, right? You understand? A high active is indicated just like the symbols that we have. It's just these basic gates that are different in the symbols that we use over here and the symbols that ISO adopted. And why they did that, I don't know. Why did they do that, Rich? I don't know. To me, once you learn these symbols, to me, these make more sense. Here, it would take you a little while, but once you learn those too. And we have a system over in, we need to take y'all one night over there and let y'all see digital and work. You know, we can do digital logic all day long until you actually see something that actually uses logic. And one of the step charts we had used this guy right here. Of course, it's pretty easy to understand that that's an AND, right? Are you okay? So these are ISO symbols. These are standard symbols. These are the symbols. Any prints you see over here are all going to do that. I have never seen a print use these ISO symbols, but I'm not going to say you're not going to run into them because they are ISO symbols. They're international standard symbols, right? Everybody okay? The AND gate requires that all inputs are high in order to get a high output. The OR gate output is high if any input is high. And an effective way to measure the precise timing relationship of digital waveforms is to use an oscilloscope or basically a logic analyzer. The problem with an oscilloscope is that if it's a standard oscilloscope is what we call a dual trace oscilloscope, which means you can only look at one, two at the same time. If you're going to look at more than two, it starts getting really complicated for the scope. And there's no way in the world you're ever going to see, unless it's a static situation. If you got pulsing inputs, for a lot of people, they'll look at an AND gate and they'll say one input is pulsing and they'll see the other input is that pulsing. And in their head, they think the what? They think the output should pulse. But if I was to come over here and then one of my symbols was, and one of my inputs on the AND gate was pulsing like this, and the other one was pulsing like this, the output will be a solid low. This is just in our bones, you know, it's hard to see that. Unless you get, if we had a scope, we could put this on there, but if we add another signal in here, and we come over here and do this, then the output would still be low, right? You understand? So on these, if you just see pulsing, which is what a logic probe is going to show you, it's going to see pulsing. They work real good for static, but they work very poor for pulsing signals. An oscilloscope works okay on 2, but if you got 3, you're messed up, right? And this is where you move into a logic analyzer, which basically shows you a lot of inputs. And so we'll pull out our logic analyzers. We got 2. One of them's fairly cheap. I don't know if they make it anymore. And then we got an HP, which is it's a logic analyzer / digital oscilloscope. So it's 2 functions on that. So it's a pretty expensive device. So on these guys, pulsing on the input, if it was an OR gate and one input was pulsing, the outputs, we know we're going to get pulses on the output, right? You understand that? An AND gate, though, you could have 8 inputs and all of them appear to be pulsing with a logic probe, but if they're not pulsing, all pulsing high at exactly the same time, the output won't change. Of course, what this chart gives you right here is, and this is what I've been trying to get across, is that we got a logic gate, and then we got what we call a family of logic. And this is this figure right here. So we got AND gates. Right now they're saying, okay, we got an inverter. Right here they're talking about a 7404. But remember, that could be a 7404. It could be a 74LS04, right? You understand that. or it could be a 74HC04. And if you was looking for the pin out, then they would be the same. A 4069 is a CMOS inverter, and it does not have the same pin out. So over here, if it's got this same sequence of numbers, what this tells you is the pin out is the same, right? Y'all understand that? By the way, used to when you saw a number start off with 74 in the old days, it meant TTL. But these guys right here changed that. So this is actually a high threshold CMOS circuit, but it has the same pin out as a what? As a 7400. So if all you need is pin outs and it starts off at a 74, then you can look up those last numbers and you can find the pin out anyway, right? What is the pin out? I've used that term a lot. What's the pin out? Very important. What's the pin out? So these are pin outs. So a pin out shows us what is assigned to every pin. It shows us what signals are assigned to these pins. Because I've got a 14-pin dip. I can pull out these dang chips over here, and we probably got 15 14-pin chips over here. And all I've got is a big black piece of plastic, 14 pins. Do they have the same pin out? No. So what do I need to do? So what does the pin out show us? The pin out shows us what signals are assigned to what pins. So this is the pin out for a 4049, which is an inverter. This is the pin out for a 7404. They're both in 14-pin dips. No, I'm sorry, this is a 16-pin dip. And look, this one power is on this pin. This one, this says NC. What do you think you see NC? What do you think that means? It means no connections. The pin is there, but there's nothing connected to it inside the package. Because these packages are standard, right? You understand? They run in twos. So usually we start off with, we go all the way down to 4 pin, but those are optical isolators. And then we get into 6 pins, and then 8 pins. Then we pick up at what? At 14 pins. So what would be the next package after 14? 16. What would be the next package? 18. What would be the next package? 20. Next package? 22. Next package? 24. Well, what they did when they went from the 14, when they went from the 22 pin, I don't see my camera application. Oh, there. When they went to the 24 pin, they changed the width. Now see that? So they went to a wider chip. This went all the way up to, this is a 40-pin dip right here. 40, yeah. I can pass these around and show you. Don't take this. These are made out of moss, and moss is susceptible to static discharge. So this is anti-static foam that would keep these guys in. Not regular foam. This is anti-static foam. The biggest chip they made in this package, in this spacing right here. But if I was to take that 24 pin and I was to place it on top of this, you'd see that these pins line up exactly. So the spacing of the pins and the width of the pins are the same. But what they did when they went from, and this is smushed. So they went from this size, when they went to 24 pin, they basically doubled the width and increased the length, right? You understand? And then they went up to 40 pin. That goes up to 40 pin. The biggest one that was ever made, by the way, on this type of was the Motorola 6800 microprocessor, and I went and cooked that out. We've got a motherboard around here that's got it. This is a 64-pin dip, and this was the last one. This was the last integrated circuit that was made in the dual line package. What they started to do after that, and we'll try to find some, is they realized right off the bat, if they shifted to a square, then they could do what? Then they could bring pins out all 4 sides. And then somebody says, well, why don't we bring the pins out the bottom? So then they came out with what they call a pin grid array, and the pins come out the bottom. And these are the guys that really do some things. And then they went to the new one that IBM, that Intel came out with. I forgot the name of it. Golly, is they took the pins off the processor and put the pins in the socket. I'll show y'all that. They say it was more reliable, but it's more expensive. It's more expensive to put all those pins on the processor. So that processor's just got all these little copper pads on the bottom of it, and the socket actually has the pins sticking up. They're spring loaded, and when you push that thing in, it pushes down on those pins. We'll show y'all one of those. So the dip, the last dip that was the last thing that used a dip as a package was the 68,000. That was the biggest one they ever made. Now they're still making dips, but that was the biggest one. That was the biggest one they ever made in the dip. It was 68,000. It was a 64 pin pack, 32 pins on each side. Are we okay? So we're working on lab. What labs are we working on? I think y'all got. 1 and 2. One was, and then we can start on another one too. I think the third lab is actually getting into basic gates. We all deal with AND gates all here. So y'all got any questions? So let me go ahead. Ask now. Questions? Y'all scared to ask me questions because y'all think I'll talk too long, right? All right, guys.